On the morning of June 30th, 1908, the remote Siberian wilderness was waking to a calm summer day. At approximately 7:17 in the morning local time, a strange, brilliant light streaked across the sky, described by witnesses as a bluish ball with a fiery tail or a diffuse glowing star. Indigenous Evenki people and Russian settlers watched in astonishment as the light moved at incredible speed across the horizon, culminating near the Podkamennaya Tunguska River. Moments later, the sky erupted in an enormous blast, generating a pillar of fire and a cloud of dark smoke. The shockwave from the explosion was so powerful that it knocked people off their feet over 60 kilometers away, shattered windows, and registered on barometers as far as England. One man, S. Semenoff, sitting on the porch of a trading post 65 kilometers from the explosion, reported being thrown several feet and feeling an intense heat that seemed to set his clothing alight. Despite the enormous energy released, estimated to be up to 1,000 times that of the Hiroshima atomic bomb, the event went largely unnoticed by the outside world due to the region's isolation and sparse population. Over the following nights, a strange atmospheric phenomenon occurred, a lingering glow in the sky across Asia and Europe, allowing people to read newspapers outdoors at midnight, signaling that millions of tons of dust and ice had been thrown into the upper atmosphere by the blast. Although the Tunguska explosion occurred in 1908, the wider scientific world did not fully investigate the event until over a decade later. In 1921, Russian mineralogist Leonid Kulik began collecting eyewitness accounts and reports, determined to uncover the truth behind what locals described as a falling star and a devastating explosion. His initial survey faced incredible challenges. The suspected impact zone was hundreds of kilometers from the nearest railway, and the Siberian wilderness was filled with dense forests, swamps, and rivers. Kulik's first attempt to reach the area failed, but he returned persistently, aided by local Evenki guides who knew the terrain intimately. By 1927, nearly 2 decades after the explosion, Kulik and his team finally reached the site. What they discovered was shocking. The forest over an area of more than 2,000 square kilometers had been flattened, yet not in a uniform manner. Trees were knocked down in a radial pattern, pointing away from a central point, creating a butterfly-shaped devastation visible even from aerial photographs years later. In the very center of the blast, however, the trees were not uprooted. They stood like scorched telegraph poles, stripped of branches and bark but otherwise intact. There was no crater, no fragments of a meteorite, and no conventional evidence of impact. The destruction was complete, yet paradoxically, the source of the energy remained invisible. Kulik meticulously documented these observations, measuring tree fall patterns and marking the radial extent of the devastation. He drained small bogs and examined depressions, suspecting impact craters, but found nothing. The more he investigated, the clearer it became that this explosion had been unlike anything seen before. An immense release of energy in midair, leaving a giant swath of destroyed forest, but no tangible object behind. This journey highlighted both the scale of the catastrophe and the enduring mystery of what had caused it. The remoteness of the Tungaska site, combined with the sheer magnitude of the destruction, delayed scientific understanding for decades. Even after Kulik's expeditions, the world had only glimpsed the enormity of the event through reports and photographs. His findings laid the foundation for decades of investigation, giving scientists the first clear evidence of an unparalleled atmospheric explosion that challenged traditional ideas of meteoric impacts and left the Siberian wilderness a silent testament to nature's raw power. After Kulik's groundbreaking expeditions in 1927, scientists began to piece together what might have caused the Tunguska event, but the puzzle was far from complete. The most widely accepted explanation that eventually emerged is known as the airburst hypothesis. According to this theory, the Tunguska object, either a stony asteroid or an icy comet, never actually impacted the ground. Instead, it entered Earth's atmosphere at an extremely high speed, estimated to exceed 50,000 kilometers per hour. The immense friction and pressure caused the object to heat up, disintegrate, and explode in midair, roughly 5 to 10 kilometers above the forest canopy. This midair explosion explains several of the baffling observations from the site. The trees at ground zero were stripped of branches and bark, but left standing, while the surrounding forest was flattened in a radial, butterfly-shaped pattern. The airburst released energy equivalent to approximately 10 to 30 megatons of TNT, hundreds of times more powerful than the bomb dropped on Hiroshima. Shock waves from the explosion were recorded by barometers as far away as England, demonstrating the extraordinary reach of the blast. Unlike typical meteorite impacts, no large fragments of the Tunguska object survived to reach the ground, which is why Kulik and later scientists could not locate a crater or recover meteorite pieces. Evidence supporting the airburst theory continued to accumulate over the decades. Analysis of tree resin and peat bog layers from the area revealed microscopic silicate and magnetite spherules, enriched with nickel, a hallmark of extraterrestrial material. Elevated levels of iridium, a rare element often associated with asteroids, were also detected in soil layers dating from 1908. Together, these findings reinforced the conclusion that a cosmic object had exploded in the atmosphere rather than striking the Earth directly. The airburst theory also gained a modern parallel with the Chelyabinsk meteor in Russia on February 15, 2013. A roughly 20-meter asteroid exploded in the atmosphere, shattering windows and injuring over 1,500 people. Though much smaller than Tunguska, the Chelyabinsk event provided a tangible example of how an object could release massive energy in midair without creating a crater. By comparing Chelyabinsk to Tunguska, scientists were able to refine their models, estimating the energy, altitude, and trajectory of the Tunguska explosion with greater accuracy. Despite this consensus, questions remained about the object's composition. Was it a dense, stony asteroid, a fragile comet, or a rare type of iron-rich meteoroid? Computer simulations suggested that a stony body between 50 and 80 meters in diameter best matched the observed damage patterns and energy release. Some researchers proposed that a large iron asteroid might have grazed the atmosphere and partially skipped back into space, but this scenario remains speculative. Regardless of the exact type, the evidence increasingly pointed to a cosmic origin and a high-altitude detonation as the explanation for the unprecedented destruction. By the mid-20th century, the Tunguska event had become a benchmark for understanding atmospheric explosions of cosmic objects. Scientists recognized that such airbursts could cause massive regional damage without leaving conventional impact evidence. The mystery of the missing crater, once baffling Kulik, was now explained by a combination of velocity, altitude, and the object's explosive disintegration in the sky. Yet even with this mainstream explanation, the event retained an aura of the strange and inexplicable, a reminder that nature could unleash incomprehensible power far above the ground, leaving almost no trace of the weapon that had done it. The Tunguska event also prompted renewed interest in planetary defense. By studying past airbursts and near-Earth objects, scientists began to understand the potential threat such events pose to populated areas. Today, Tunguska serves as both a historical oddity and a cautionary tale, a cosmic event capable of leveling vast tracts of forest, demonstrating the fine line between natural wonder and catastrophic destruction. Even with the airburst hypothesis providing a solid scientific explanation, the Tunguska event continued to fascinate and confound both scientists and the public, inspiring numerous fringe theories. The lack of a crater and the near total disappearance of the object left room for speculation that ranged from the imaginative to the outright fantastical. One of the most enduring ideas was that the explosion had been caused by a crashing extraterrestrial spacecraft. Sci-fi author Alexander Kazantsev, writing after the atomic bombings of Hiroshima and Nagasaki, suggested that a UFO powered by a nuclear engine might have detonated over Siberia. He pointed to the radial destruction pattern and the intense energy release as evidence, comparing it to a small-scale nuclear explosion. While visually compelling, there is no empirical evidence to support this claim, and it remains purely speculative. Another proposed explanation involved exotic physics. In 1973, some physicists hypothesized that a miniature black hole could have passed through the Earth at Tunguska, creating a catastrophic shockwave without leaving any conventional impact evidence. In this scenario, the black hole would have entered the atmosphere, released an immense amount of energy, and exited on the opposite side of the planet. Although theoretically testable, predicting disturbances or energy signatures at the exit point, no such evidence was ever observed, making this idea extremely unlikely. A third, equally speculative theory involved antimatter. Scientists proposed that a small chunk of antimatter might have collided with the Earth, annihilating itself and releasing enormous energy while leaving no debris. In practice, large amounts of antimatter do not naturally exist in our solar system, making this explanation virtually impossible. yet it persisted in popular discussions, largely because it accounted for the total disappearance of the object. Even Nikola Tesla was pulled into the conversation. Some conspiracy theorists claim that Tesla had been testing a long-range wireless energy weapon, a death ray, and that the Tunguska blast was an accidental discharge directed at the unpopulated Siberian wilderness. Proponents imagine that Tesla had attempted to bounce massive electrical energy off the ionosphere and inadvertently triggered the explosion. While this theory is dramatic, there is no credible historical evidence linking Tesla to the Tunguska event, and it remains a modern myth. Other ideas included natural but unusual phenomena, such as a massive volcanic gas explosion from a previously unknown Siberian vent, or a sudden release of methane from permafrost. Both were largely discounted because no supporting geological evidence was found, and the radial tree fall pattern matched a high-energy aerial explosion rather than a ground-based release. Despite the lack of supporting evidence, these fringe theories served an important role in the public imagination. They highlighted how a single unexplained event could challenge conventional thinking and spark creative, if scientifically unsupported, explanations. The combination of immense power, the absence of physical remnants, and the sheer isolation of the event contributed to Tunguska's reputation as one of the weirdest events in recorded history. Ultimately, while these alternative explanations are intriguing, they cannot compete with the airburst hypothesis, supported by modern measurements, chemical analysis, and computer modeling. Nevertheless, the persistence of these ideas illustrates the deep human desire to understand mysteries that seem almost supernatural. Tunguska became more than just a historical explosion. It became a symbol of the unknown forces that lurk above our planet, waiting for a rare, devastating moment to remind humanity of its vulnerability. After more than a century of study, the scientific consensus has largely settled on the Tunguska event being caused by the airburst of a cosmic body, likely a stony asteroid or comet, that exploded in the atmosphere without ever touching the ground. Detailed computer modeling suggests the object was between 50 and 80 meters in diameter and detonated with the energy of 10 to 30 megatons of TNT. This mid-air explosion explains the unique butterfly pattern of flattened trees, the standing but scorched trees at the epicenter, and the absence of a crater. Subsequent expeditions to the site uncovered tiny silicate and magnetite spherules embedded in soil and tree resin. These microscopic spheres contained elevated levels of nickel, a classic indicator of extraterrestrial origin. Analysis of peat bogs in the region also revealed a distinct layer dating to 1908 with higher than normal concentrations of iridium, an element rare on Earth but common in meteorites. These findings strongly support the hypothesis that a cosmic object entered Earth's atmosphere and exploded, leaving only trace evidence of its presence. The Chelyabinsk meteor in Russia, which exploded in February 2013, provided a modern analog. At about 20 meters in size, it created a powerful airburst that shattered windows and injured over 1,500 people, demonstrating on a smaller scale how a fast-moving object can release enormous energy in the sky. Scientists now understand that such airbursts can flatten forests, create shockwaves over hundreds of kilometers, and produce bright, lingering atmospheric effects without leaving a crater. Debate continues over whether the Tunguska object was a comet composed mostly of ice or a denser, rocky asteroid. Some models suggest that a cometary body would account for the bright, glowing skies observed across Europe and Asia for several nights after the explosion. However, most recent analyses favor a stony asteroid, based on calculations of density, entry angle, and energy release, which better explain the pattern of destruction observed in the Tunguska forest. Beyond solving the mystery of Tunguska itself, this event has become a crucial case study for planetary defense. Scientists use the data to model potential near-Earth object impacts, simulate atmospheric explosions, and develop early warning systems. Tunguska illustrates that even relatively small cosmic objects can unleash destruction comparable to the largest nuclear weapons. The event also serves as a cautionary reminder of how rare but high-impact cosmic phenomena can threaten human civilization. It underscores the need for continued investment in asteroid detection, monitoring, and, if necessary, deflection technologies. International efforts, including NASA's DART mission and other planetary defense initiatives, aim to prevent future disasters on a global scale. While the mystery of Tunguska has largely been resolved scientifically, Its legacy continues to inspire awe, caution, and curiosity. It reminds humanity that Earth is not isolated from the cosmos, and that even the most remote and sparsely populated regions are vulnerable to forces far beyond human control. Tunguska remains a singular example of a natural event that is as educational as it is terrifying. The Tunguska event of June 30th, 1908 remains one of the most bizarre and unsettling occurrences in modern history. While scientists have largely confirmed that a mid-air explosion of a cosmic object caused the devastation, the sheer scale and unusual characteristics of the event continue to capture imaginations. From the flattened forests over 2,000 square kilometers to the standing but scorched trees at ground zero, every detail underscores the extraordinary force released by the explosion. The event also serves as a stark reminder of humanity's vulnerability to cosmic hazards. Objects in space, even relatively small ones, can release energy equivalent to dozens of nuclear bombs without warning. Had the Tunguska object exploded over a populated city instead of the remote Siberian wilderness, the consequences could have been catastrophic, potentially killing tens of thousands and causing unimaginable destruction. This scenario illustrates why planetary defense is not just theoretical. It is a real, urgent priority for scientists worldwide. Since Tunguska, international space agencies have invested heavily in detecting and tracking near-Earth objects. Programs like NASA's DART mission, which successfully altered an asteroid's trajectory, show that technological solutions exist to mitigate potential threats. Additionally, global awareness campaigns such as International Asteroid Day on June 30th educate the public about the dangers of space hazards and the importance of scientific monitoring. The Tunguska explosion also continues to fuel curiosity and debate. Fringe theories, from alien spacecraft to miniature black holes, may have no scientific basis, but they highlight how a mysterious event can inspire both wonder and speculation. In reality, the true story is compelling enough: a cosmic visitor traveling millions of kilometers through space, disintegrating in our atmosphere, and leaving behind a scar on the Siberian forest that remains visible more than a century later. Even today, researchers revisit the Tunguska site, studying tree rings, soil layers, and atmospheric data to refine models of airburst phenomena. These investigations help predict how similar events might unfold and improve our understanding of the physics behind cosmic explosions. Every new piece of data reinforces the lesson that Earth exists in a dynamic and sometimes dangerous cosmic environment. Ultimately, the Tunguska event is a reminder of both the fragility and resilience of life on Earth. While it exposed how vulnerable human settlements can be to rare cosmic phenomena, it also prompted scientific innovation and preparedness that could save countless lives in the future. By studying the past, humanity learns to anticipate and survive potential threats from beyond our planet. The legacy of Tunguska is therefore twofold: a chilling historical record of one of nature's most powerful airbursts, and a continuing call to vigilance, research, and planetary defense. It is a story of mystery, destruction, and scientific triumph, an event that transformed a quiet Siberian wilderness into a cautionary tale for the entire world. The memory of that bright, terrifying morning on June 30th, 1908, remains etched into both the Earth and human consciousness, serving as a final warning from the cosmos itself. On the morning of February 15, 2013, the city of Chelyabinsk in southern Russia was settling into a normal winter day. Temperatures were well below freezing, the sky was clear, and people were commuting to work, sitting in traffic, or already inside schools and offices. Nothing about the calm atmosphere suggested that Earth was about to be struck by the most powerful space impact event in more than a century. Unknown to scientists and astronomers around the world, a small asteroid was already racing toward the planet at extraordinary speed. Just after 9:20 in the morning local time, the sky suddenly erupted in light. A brilliant fireball tore across the atmosphere, so bright that it briefly outshone the sun itself. The flash was intense enough to cast sharp moving shadows across buildings, streets, and snow-covered ground. Many eyewitnesses later said they instinctively turned away or shielded their eyes, believing for a split second that a massive explosion or even nuclear detonation had occurred. Some people reported feeling a brief sensation of heat as the object passed overhead, despite it being many miles above the surface. So what made this moment especially unique was how well it was documented. Dash cameras, commonly used in Russian vehicles for insurance purposes, captured the event from dozens of angles. These recordings show a small bright point streaking across the sky, rapidly growing into a blinding white flare, followed by a long, twisting smoke trail that lingered in the cold air. For nearly 2 minutes after the flash, there was an eerie silence. The meteor had already exploded high in the atmosphere, but the sound had not yet arrived. During this pause, many people stepped closer to windows or went outside to look at the strange cloud stretching across the sky. That decision would prove dangerous. When the shock wave finally reached the ground, it struck with tremendous force. The pressure wave shattered windows, cracked walls, and slammed doors open across a wide area. The blast was strong enough to be later compared to a magnitude 4.2 earthquake, even though no fault had moved beneath the city. This initial moment marked the true beginning of the Chelyabinsk disaster. The asteroid itself never touched the ground, but in just a few seconds, it transformed an ordinary winter morning into chaos. What followed would leave thousands injured, entire neighborhoods damaged, and scientists around the world scrambling to understand just how large and powerful this unexpected visitor from space had been. When the delayed shockwave finally swept across Chelyabinsk and the surrounding region, its impact was immediate and widespread. The pressure wave traveled outward for hundreds of miles, striking cities and towns across 6 different administrative districts. Buildings shook violently, alarms sounded, and glass burst inward with explosive force. Unlike an earthquake, which ripples up from the ground, this blast came from above, catching people completely off guard and giving them no chance to brace for impact. The most severe damage was caused not by collapsing structures, but by shattered windows. Thousands of panes of glass failed at once, sending razor-sharp fragments flying into homes, classrooms, offices, and factories. More than 7,000 buildings were damaged, including apartment blocks, schools, hospitals, and industrial facilities. In some areas, entire building facades were stripped of glass. At a large zinc processing plant on the outskirts of the city, a massive section of the roof collapsed under the force of the blast, narrowly missing workers inside. Hospitals quickly began filling with injured residents. Nearly 1,500 people sought medical attention in the hours that followed, most suffering from cuts, bruises, concussions, and eye injuries caused by flying debris. Children were especially affected, as many had been standing near windows in schools after seeing the bright flash in the sky. Despite the scale of the event, no fatalities were reported, a fact largely attributed to the high altitude of the explosion and the structure of modern buildings absorbing much of the force. The freezing winter conditions made the situation even more dangerous, with outdoor temperatures hovering well below zero. Tens of thousands of apartments were suddenly exposed to the cold after their windows were destroyed. Emergency crews and volunteers worked around the clock to board up broken openings with plastic sheets, plywood, and cardboard. In total, more than 100,000 residents were left dealing with damaged homes in sub-zero weather. As local authorities assessed the destruction, a larger realization began to take hold. This was not a conventional disaster. No storm had been forecast, no seismic warnings had been issued, and no sirens had sounded beforehand. The damage had come from space, delivered without warning, and it raised a critical question that scientists and governments would soon begin asking in earnest. If an object this small could cause this much destruction, just how large was the Chelyabinsk meteor that triggered it all? With the immediate chaos under control, scientists turned their focus skyward, beginning a detailed investigation to understand exactly what had struck Earth. The Chelyabinsk event quickly became one of the most thoroughly studied cosmic impacts in human history, thanks to an unprecedented amount of accidental data. Dash cameras, security systems, traffic cameras, and even handheld phones had recorded the fireball from dozens of angles, giving researchers a rare opportunity to reconstruct the event second by second. By analyzing these videos frame by frame, scientists were able to calculate the meteor's speed, angle, and breakup sequence. The object entered Earth's atmosphere traveling at roughly 19 kilometers per second, moving faster than any rifle bullet and carrying an enormous amount of kinetic energy. Its trajectory was shallow, skimming through the upper atmosphere rather than plunging straight down, which allowed it to travel hundreds of kilometers before finally disintegrating. Using global infrasound sensors designed to detect nuclear tests, researchers measured the energy released during the explosion. These stations, spread across the planet, recorded a powerful low-frequency pressure wave that circled Earth multiple times. From this data, scientists determined that the airburst released energy equivalent to several hundred kilotons of TNT, making it dozens of times more powerful than the atomic bomb used in World War II. Yet unlike a nuclear detonation, the energy was spread over a wide area, reducing the likelihood of total structural collapse. From these combined measurements, the true size of the object began to emerge. The meteor was estimated to be between 17 and 20 meters in diameter, roughly comparable to a multi-story building. Its mass was calculated at around 10,000 metric tons, composed primarily of ordinary chondrite material, one of the most common types of stony asteroid found in the solar system. This classification helped scientists understand how and why it fragmented so violently under atmospheric pressure. As fragments rained down, a search began across the snowy landscape south of Chelyabinsk. Small blackened stones were soon discovered embedded in ice and frozen soil, each bearing the unmistakable fusion crust formed during atmospheric entry. The largest surviving piece was later recovered from the bottom of a frozen lake, confirming that while the atmosphere absorbed most of the meteor's energy, it had not completely destroyed the intruder. Instead, Earth had captured physical proof of the event, offering scientists a direct sample of the object that had caused such widespread disruption and setting the stage for a much larger conversation about planetary vulnerability. As researchers pieced together what had happened over Chelyabinsk, one unsettling question dominated the discussion. Why had no one seen it coming? This was not a failure of technology in the usual sense, but a limitation of where and how humanity watches the sky. The meteor approached Earth from the direction of the sun, a region that ground-based telescopes cannot safely observe. Against the overwhelming glare of daylight, the object was effectively invisible until it was already tearing through the atmosphere. This realization exposed a dangerous gap in planetary monitoring. At the time, most asteroid detection efforts were focused on identifying massive extinction-level objects, the kind capable of wiping out entire regions or even civilizations. Smaller asteroids, those tens of meters wide, were considered a lower priority because they were not expected to cause widespread devastation. Chelyabinsk proved that assumption wrong. While the meteor did not leave a crater or level the city, it injured more than 1,000 people and caused extensive damage across a densely populated area. The event immediately drew comparisons to the Tunguska explosion of 1908, another atmospheric airburst that flattened a vast forest in Siberia. The crucial difference was location. Tunguska occurred over a remote wilderness, while Chelyabinsk unfolded over a modern city filled with glass, concrete, and people. For the first time, scientists and emergency planners had real-world data showing what a mid-sized asteroid could do to an urban environment. In the months that followed, space agencies and governments reassessed their approach to near-Earth objects. Detection programs were expanded, and new emphasis was placed on finding smaller asteroids that could still pose a serious threat. International cooperation increased, with data sharing between observatories becoming faster and more coordinated. The idea that asteroid impacts were rare, abstract events belonging to deep time was replaced by a more urgent understanding that they are an ongoing natural hazard. Chelyabinsk also reshaped public awareness. Unlike ancient impacts known only through geology, this disaster was witnessed in real time by millions through video footage shared across the world. The sudden flash, the delayed shockwave, and the shattered windows made the danger feel immediate and personal. By revealing how vulnerable even a modern city could be, the Chelyabinsk meteor transformed planetary defense from a niche scientific concern into a global conversation about preparedness, setting the stage for the final lessons that would emerge from this extraordinary event. In the years after the Chelyabinsk meteor, scientists continued to study the physical evidence it left behind to better understand how such objects behave during atmospheric entry. Fragments recovered from the surrounding region revealed that the meteor was a stony chondrite, one of the most common types of space rock to strike Earth. Laboratory analysis showed signs of extreme pressure and heat, confirming that the object fractured violently rather than surviving as a single mass. These findings helped refine models that predict how similar asteroids might break apart in the future. The event also influenced how risk from space is communicated to the public. Chelyabinsk demonstrated that even without an impact crater, an airburst can cause widespread injuries and infrastructure damage. Emergency planners began incorporating asteroid airbursts into disaster response scenarios, alongside earthquakes, severe storms, and industrial accidents. Public education efforts increasingly emphasize simple protective actions such as staying away from windows after a bright flash in the sky, lessons directly informed by what unfolded over the city. On a global scale, Chelyabinsk became a benchmark for planetary defense planning. Space agencies used the data to justify new survey missions designed to detect near-Earth objects earlier and from vantage points that can observe closer to the sun. These efforts aim to provide days, weeks, or even years of warning for future threats, transforming surprise events into manageable risks. The meteor's relatively modest size underscored a critical truth: danger from space does not require a world-ending asteroid to have serious consequences. More than a decade later, Chelyabinsk remains the most well-documented asteroid airburst in human history. It stands as a rare moment when a cosmic event intersected directly with everyday life in the modern world. Dashcams, security cameras, and satellite sensors captured a natural phenomenon that once would have passed into legend, turning it instead into a scientific case study. Ultimately, the Chelyabinsk meteor answered the question at the heart of this story. It was not massive enough to end civilizations, but it was large enough to injure thousands and shock the world. Its legacy is a clearer understanding of Earth's place in a dynamic solar system, and a reminder that space hazards are not just relics of the past, but real forces that continue to shape our present and future. On the morning of February 12, 1947, the Sikhote-Alin mountain range in eastern Siberia was locked in deep winter. Snow covered the forest, temperatures were well below freezing, and the region was sparsely populated by loggers, hunters, and small rural settlements. At approximately 10:38 in the morning local time, that quiet routine was shattered by a sudden, blinding light that tore across the sky. Eyewitnesses described a fireball so bright it rivaled the sun, forcing people to shield their eyes or turn away in fear. The object streaked from north to south, leaving behind a thick, white smoke trail that twisted and expanded as it drifted in the cold air. Moments later, a series of thunderous explosions echoed across the mountains, loud enough to rattle windows and knock people off their feet. Some observers reported feeling a wave of heat on their faces despite the freezing conditions, a result of the intense energy released as the object tore through the atmosphere. What made this event especially terrifying was how low it happened. The fireball did not burn up quietly high above the Earth. Instead, it penetrated deep into the atmosphere before violently breaking apart. As it fragmented, glowing pieces peeled away from the main mass, continuing toward the ground at extreme speed. To those watching from below, it looked as if the sky itself had shattered. Then came the fallout. Metal fragments began raining down over the forest, crashing through tree branches and slamming into the frozen ground. The sound was described as roaring, cracking, and whistling, followed by heavy impacts that sent tremors through the earth. In some areas, the falling debris ignited small fires as it struck dry wood beneath the snow. For hours after the explosion, a long plume of dust and smoke hung in the sky, stretching for tens of kilometers and slowly dispersing in the winter air. People across the region knew they had witnessed something extraordinary and deeply unnatural. Unknown to them at the time, this was the largest witnessed iron meteorite fall in recorded history, and the beginning of one of the most important scientific investigations of the 20th century. When the explosions finally faded and the sky began to clear, the true scale of what had happened in the Sikhote-Alin mountains slowly revealed itself. Deep within the taiga, an enormous stretch of forest had been violently transformed. Trees were snapped, stripped of branches, and flattened in chaotic patterns that pointed back toward the sky. The ground itself was scarred, punched, and torn open as if struck by artillery fire. The meteorite fragments did not land in a single spot. Instead, they were scattered across an elongated, elliptical impact zone measuring more than 1 square kilometer. Within this area, scientists would later document well over 100 impact craters, ranging from small fist-sized pits to massive gouges in the frozen earth. The largest crater measured roughly 26 meters across and plunged more than 6 meters deep, its edges sharp and raw from the force of impact. What puzzled early observers was the strange relationship between crater size and fragment size. Some of the largest craters contained only tiny pieces of metal, while smaller craters sometimes held massive chunks weighing hundreds of kilograms. The forest floor was littered with twisted iron, shards, jagged slabs, and compact metallic masses, unlike any rock native to the region. Many fragments were still partially embedded in the ground, surrounded by splintered roots and frozen soil thrown outward by the impact. Local residents and forestry workers were among the first to reach the area. They described the scene as resembling a battlefield, with metal scattered everywhere and trees damaged in all directions. The fragments were astonishingly heavy for their size, instantly setting them apart from ordinary stone. Some pieces showed sharp, torn edges, as if ripped apart by extreme force, while others appeared smoother and more rounded, darkened by intense heat. Within days, news of the event reached scientific authorities. Reports of metallic debris falling from the sky, combined with eyewitness accounts of a massive fireball and explosions, made it clear this was no ordinary atmospheric phenomenon. The Soviet scientific community quickly realized the importance of the site. Preparations began for an official investigation, as researchers understood they were dealing with an exceptionally rare and well-preserved meteorite fall. The Sikhote-Alin forest had become a natural laboratory, frozen in time. Every crater, every fragment, and every damaged tree held clues about the object's violent descent. What caused such a powerful breakup, so close to the ground? And what exactly was this mysterious iron raining from the sky? Those questions would soon drive one of the most ambitious meteorite expeditions ever undertaken. As reports from the Sikhote-Alin impact zone continued to pour in, the scale of the event became impossible to ignore. Later that same year, the Soviet Academy of Sciences organized a full-scale scientific expedition to the remote crash site. The mission was led by Academician Burbunsa Vladimir Grigorievich Fesenkov, one of the leading astronomers of the era, and it marked one of the most ambitious meteorite investigations ever attempted. Reaching the site was an ordeal in itself. Scientists traveled by rail to the farthest accessible settlements before continuing on foot, skis, and sleds through deep snow and rugged terrain. Supplies had to be hauled across frozen ground and progress was slow. Once in the impact zone, the team established field camps and began the painstaking task of mapping craters, cataloging damage, and recovering fragments scattered throughout the forest. A crucial part of the investigation involved collecting eyewitness testimony from villages spread across the region. Hundreds of people had seen the fireball streak across the sky, heard the explosions, or felt the ground tremble. By comparing the timing, direction, and intensity of these reports, researchers were able to reconstruct the meteorite's flight path through the atmosphere. This data allowed them to determine the angle of entry and the general direction the object had traveled before breaking apart. As fragments were collected and examined, scientists noticed a clear pattern. The recovered material fell into two distinct categories. One group consisted of sharp, jagged pieces with torn edges, often twisted and irregular in shape. These fragments showed signs of violent mechanical breakup, indicating they were ripped apart during the low-altitude explosion or shattered upon striking the ground at high speed. The second group looked very different. These pieces were more compact and rounded, with smooth, darkened surfaces. Many displayed shallow, thumbprint-like depressions, formed as their outer layers melted and ablated during flight. These features revealed that some fragments had separated earlier and traveled longer through the atmosphere, slowing down before impact. This discovery was a breakthrough. It showed that the Sikhote-Alin meteorite did not simply explode once, but fragmented in multiple stages during its descent. Each stage produced different types of debris, leaving behind a complex and revealing pattern on the ground. Over successive expeditions, scientists would recover more than 23 tons of material, creating an unprecedented collection for study. What began as a terrifying spectacle in the sky had now become a meticulously documented scientific event. With eyewitness accounts, now crater maps, and thousands of kilograms of recovered metal, researchers finally had the evidence needed to answer the most important question of all. What exactly was this object, and where did it come from? With thousands of recovered fragments now in laboratories, scientists could finally focus on the meteorite itself. Detailed chemical testing quickly revealed that the Sikhote-Alin object was an iron meteorite, not a stony one. Its composition was dominated by iron, with a significant amount of nickel, along with smaller traces of cobalt, phosphorus, and sulfur. This explained why the fragments were far heavier than ordinary Earth rocks, and why so many pieces survived the violent descent. When researchers cut and polished several specimens, an extraordinary internal structure appeared. Etching the metal with acid exposed a distinctive interlocking crystal pattern known as the Widman-Staughton pattern. This structure can only form when molten metal cools at an incredibly slow rate. measured in degrees per million years. Such conditions exist deep inside large asteroids, but nowhere on Earth. This pattern provided definitive proof that the Sikhote-Alin meteorite originated in outer space and was once part of a much larger body. Using trajectory data reconstructed from eyewitness reports, shockwave timing, and crater distribution, scientists calculated the object's path before it entered Earth's atmosphere. Their results showed that the meteorite had been traveling on an elongated orbit around the Sun. This orbit traced back to the asteroid belt located between Mars and Jupiter, a region known for frequent collisions between large rocky bodies. The evidence suggested that the Sikhote-Alin meteorite was a fragment from the metallic core of a parent asteroid that had been shattered in a collision millions of years earlier. Over vast spans of time, gravitational interactions slowly altered its orbit until it crossed Earth's path. What fell over eastern Siberia was not just a random space rock, but a remnant of an ancient planetary building block. This realization marked a major scientific milestone. For the first time, researchers could directly connect telescopic observations of asteroids with physical samples recovered on Earth. Sikhote-Alin became a critical link between cosmic theory and tangible evidence, proving that meteorites are literal pieces of other worlds. By the end of the analysis, the event was no longer just a historical curiosity, but a cornerstone in the study of planetary formation and near-Earth hazards. This Sikhote-Alin meteorite fall remains unmatched as the largest witnessed iron meteorite event in recorded history. Scientific estimates suggest the original object weighed close to 100 metric tons before entering Earth's atmosphere. Even after the violent breakup and airburst, tens of tons of material survived and struck the ground, an extraordinarily high survival rate compared to most meteorite events. This sheer mass is what made the event so scientifically valuable and so physically destructive. Unlike stony meteors that often disintegrate completely, the dense iron composition of Sikhote-Alin allowed fragments to reach the surface at tremendous speed. This created a crater field unlike anything previously studied in real time. Researchers discovered an unusual pattern during excavations. Some of the largest craters contained only tiny metal remnants, while smaller craters sometimes held massive chunks. The conclusion was striking. The largest fragments hit with such force that they partially vaporized on impact, while smaller pieces slowed enough to survive intact. When scientists compared Sikhote-Alin to other historic cosmic events, its uniqueness became clear. It released less total energy than the Tunguska explosion of 1908 and far less than the Chelyabinsk airburst of 2013. However, neither of those events delivered anything close to the amount of recoverable material that Sikhote-Alin did. This made it a once-in-a-lifetime natural experiment, allowing scientists to study crater formation, fragmentation physics, and atmospheric entry behavior using real-world evidence. The meteorite also reshaped how scientists understood asteroid threats. Sikhote-Alin demonstrated that iron-rich asteroids behave very differently from stony ones during atmospheric entry. This insight became crucial for later planetary defense models, helping researchers predict how different types of near-Earth objects might break apart or survive if they were ever on a collision course with our planet. Today, Sikhote-Alin fragments are housed in major museums and research institutions around the world. Some pieces still bear sharp, torn edges from the explosion, while others display smooth, sculpted surfaces formed during flight. Each fragment is a physical reminder that Earth is not isolated from space, but part of an active and evolving solar system. The fall of the Sikhote-Alin meteorite was not just a strange event from the past. It was a turning point in planetary science, proving that cosmic disasters can be studied, understood, and prepared for. Long after the smoke trail faded from the Siberian sky, the impact of that iron rainstorm continues to shape how humanity looks upward, knowing that pieces of the universe can, and sometimes do, fall straight into our world,